So let's get started. Okay, so I'm going to give you an overview of the key elements of the architecture. You'll be exploring it today. This is sort of the gratuitous marketing slide. It's maybe it's not too gratuitous, but you know, we just want to confirm that we see an insatiable need for performance. The algorithms up here are from the oil and gas industry, and they already know that they could use an exaflop machine. I'm sure all you guys could figure out that you need an exaflop machine as well, but everyone says, oh, it's going to tail off. You don't need to do all this. Our view is we're probably not doing enough, and that's hence why this growth and the complications of that growth, in particular for power, as David was saying yesterday, the memory speeds, the interconnects are not going at the pace of flops. So I'm not going to say flops are free. I don't think I can say that for Intel. But delivering the whole package is really what we're looking at as well. I'm not going to talk about it much, but Intel, you may have heard that Intel has made significant investments in the last year in interconnect, both essentially acquiring QLogic and then also acquiring the Aries InfiniBand capability from Cray and some of their people. At least I don't know if that's closed yet, but it's been announced. So we're looking at all aspects. But you know, we see no end to the use of, again, both traditional Xeon usages, and then for key power performance improvements, the mic architecture is what we're driving in that area. Pretty much just said it. The Xeon's the foundation. You've all used this architecture. It can handle the full scope of workloads. It has parallel capability. It has serial capability. Enhanced. Great processor. Most people have great usage of that, including the number 4. The number 4 system is an all Sandy Bridge system, you know, from Europe. The number 1 European system is a full Sandy Bridge Xeon alone system. Just was announced, highly efficient, both power and compute optimized. Xeon Phi, you'll hear this over and over again. Highly parallelized workloads. If you don't have a highly parallelized workload, or it can't be, Phi is not there. Another huge point which we'll continue to hammer home, James will jump on it, is the common programming model. You know, there are nuances about the architecture, and David was showing different architectures yesterday, different levels of cache and all that. But fundamentally, we want the experience to be the same. What you've learned to evolve into the usage, not jumping on another path, a brand new interface, or other mechanisms in order to leverage that. It's difficult, but that's one of our goals. And then again, I already repeated, 22 nanometer is the same process that Ivy Bridge is coming out on, and Knights Corner is coming out on that process as well. And the greater than 50 cores, as I said, and again, we haven't said exactly what our product SKUs will have or how many SKUs there will be. So just terminology, Knights Ferry, I already mentioned it. That was an early development platform. I can tell you that we had 2 SKUs of that, both active. See the active fan there. 30 and 32 cores is what we had. That's been well publicized. Knights Corner, again, all these things I showed what the announcement was. They are PCIe cards. They are double wide and GDDR. And then future Knights is how we refer to what might happen next. So what did we do? You know, how did we get where we got? So we started with these things we call smaller cores and smaller in-order capability. Took a lot of the serial performance out so we could leverage that. And obviously, that allowed us to add many processing cores to our silicon. To that, we added very wide vector units. I think we can say it's 512 because it's in the document. So it's double what the maximum AVX size is. And multi-threading. We don't call it hyper-threading in this part. We call it multi-threading. There's some interesting differences between the two. But more threads to take advantage of the memory bandwidth, the latencies that might occur. It's not a panacea. We don't. So what we're finding is most workloads benefit from 2 to 3 threads per core, depending on how you do it. This technology will currently for Knights Corner will do up to 4 threads per core. You have to be careful how to use it. Michael will be talking about that, I believe. But the way I look at this is, again, we dial up the contrast for parallel computing. We put a device out there to push people or to engage with the growing need to leverage parallel computing. And this is a high contrast for that. And of course, the contrast is against Xeon, which obviously has multiple cores and capabilities. But we're talking heavy scaling use, heavy threading, basically parallel on steroids, basically. These are some of the markets that we're attacking. It doesn't mean, or that are appropriate for it. We already mentioned energy, even digital content creation. We have some work going on with DreamWorks there. Climate modeling, a lot of people have talked about that. So all these markets, which you guys know well. I don't think we've showed this slide publicly before. And it doesn't tell you a ton. This is a very similar slide, actually, to David's, to some of David's yesterday. But this is a single chip silicon overview. These are the key interfaces. This isn't a pure layout look or whatever, but we've got multiple cores. We have the IPN stands for interprocessor network. That's how they talk to each other and communicate across. And then we have memory controllers that go out to memory. We have a PCIe interface. It's a PCIe target device. And essentially, and I think Neil, you were talking about SMPs, right, or David? We view it as an SMP on a chip. It has a network of capability to communicate with each other. It has caches for each, and then they can be ganged together to operate as a uniform cache. And we built this for scalable performance. The other key thing, and we'll talk about this a little bit today, it's the PCI interface has a DMA engine. It is fully capable of peer-to-peer transfers between its own cards and third-party cards. Magic sort of comes in the software that utilizes it and what capabilities are there, but it can do peer-to-peer direct transfers without involving the host other than the host's I/O hub. So what's kind of a snapshot of the whole environment? We've got this optimized highly parallel coprocessor, now called Intel Xeon Phi. Knights Corner is the first version. It does run complete applications. It has an operating system. It's Linux. You will see today that you can shell over to the card. It's its own compute node. It's on the network. You can arrange it in a local, sort of static local environment, or you can arrange it cluster-wide to be visible. Again, we have the common source code. Again, you should see today combinations of the styles we use, but you certainly can port a code. And many of our customers I say an hour, it could be 5 minutes. I don't know what you found, depending on the code. You just do a switch, target mic, then you just use it as a node, copy it over, and you can just run. Doesn't mean it's going to run fantastic. If it has lots of serial stuff, it's not parallelized. It may run even worse than on a Xeon until you look at the tuning and some of the techniques we're going to show today. but indeed you can get started with your data-driven analysis and optimization from the moment you engage with one of these parts. It does support the standard models of clustering. I'm going to go over that a little bit. You know, it builds on the advances that we've done at Intel in both software and development tools, and on our knowledge of parallelism with multi-core, wrap them all together, and this is what we've got. So in the environment, it acts as its own SMP compute node. Now I'm going to jump into some of the terminology and what we use to describe the environment, how it fits, how we did what we did in order to make it a compute node, and then some of the usage models. So really the software package at a high level involves two major areas. Are what we call our development tools. These are what you're used to, the ICC, the libraries, MPI, all those capabilities. To those tools, we added something called language extensions for offload. That's what I would call one of the programming models we support. It's not the only one, but this is the model where you have sections of code that you want to offload, but you want to purely manage it as an executable on the host. It works in that mode. It's leveraging that whole compute node thing in the background, but it's a directive-based mechanism. And then the other half is sometimes we just call them the drivers, but there's a whole lot more to it than that, is the Mike platform software stack. So as you engage with Intel, you might hear us use the acronym MPSS, Mike platform software stack. That's the Linux operating system, and then everything around it, both host and Mike side, to enable its use. So these are driver level interfaces. As I said, we call it the micro OS internally. It's sort of an embedded Linux based. It's not, you don't do Red Hat on this thing, but the kernel's based on 2.6.34 kernel that we've modified to boot on the Mike device, basically. This enables us, by using Linux in this environment, this is really what enabled us. Linux is fundamentally a network operating system. All the standards you're used to just work. We're not going to give you a special Mike command to talk to it. You're going to SSH to the device or telnet to the device. All that stuff works. We do have a new term here, symmetric communication interface driver, SKIF. That's pretty much the lowest level we would recommend anyone ever deal with the card at. It's essentially a light layer that's communication oriented. It actually looks a fair amount like sockets, but it's a layer over top of the DMA engine essentially, and also you can map memory as well. That's the mechanism, and most of our capability is built on top of SKIF as far as communicating and pushing data around. And then we do have some middleware interfaces that are targeted to tools vendors. We don't think very many application vendors would use them. Our own tools use these interfaces. So we're not going to talk much about those today. I don't think anyone's really a tools vendor in here. Our design goals in building this this environment is to support a wide range of enable for me to stand up in here and say, hey, it's Intel architecture, it's x86, it's what you're used to. We can support a lot of interesting usages with this model, which we'll talk about. It's standards compliant, and then we obviously want scalability. And then we have this thing called Symmetry, which I'll tell you about in a second. It's hopefully become obvious. Bottom line is we wanted a broad range because not every workload, not every application, not every system is the same. You need that flexibility. I'm going to try to explain the symmetry now, the notion of the symmetry. If you look at this diagram, we're essentially trying to block out the environment. The left side is the host. The right side is the card or the Xeon Phi coprocessor. The dotted line you can is distinguishing between the two, and they're connected via PCI Express. And I don't really want to go into every little item here that you can see. Really, what you should say is, geez, both sides look almost exactly the same, right? Why'd you put up a diagram with two things? We have structured this so that, again, when you engage with the coprocessor, engage with the Xeon Phi, you're not engaging with something new. It's what you're used to. It's symmetric in the sense that there's a mirror image, essentially, in your mind. When you work with it, you don't have to think about that it's different. You think about that it's the same. Maybe there's subtle differences. The yellow is the Linux Micro OS. That is not a Red Hat or CentOS or whatever. But most of the things you need are there. And the beauty of it is if there's something that's not there, you can add it. If there's a library, if there's an interface, if there's something that exists that would come in a normal distribution, we give you all the tools to compile that, either link it into the kernel, or of course, user mode libraries. So you can extend or limit the environment as you need for your capabilities. And the only other probably interesting thing that you might not jump out at you is the fact that we actually have a DAPL OFED layer capability right on the device. So, and our MPI is built on top of that. And we'll talk about that a little bit more in a second, but just keep that in mind. Sockets work, you know, most of the programming models that you're used to, both high and low. So if you saw what our goals were, this is kind of what we came up with to do it. Just to kind of hammer it home, just the differences is, you know, a Xeon typically will support all this stuff on the left from an environment standpoint. We have some gaps. We don't have OS X or Windows running on the device, and there's obviously, you know, those are, you know, highly visually oriented. This is not a visual workstation. So even though it's a peripheral device, feels like a peripheral device that you could go to Fry's or something and buy, you're not going to buy it that way. You're going to buy it from HP. You're going to buy it. So it's going to be an integrated platform. So it does need validation in a platform. It's PCI compliant and capable, but we're only going to work with OEMs who validate it in a total configuration. Pretty complex thing. We want to make sure it works when you buy it. Just to round it up, it's sort of similar. This is just a different look at the previous one. VE stands for Virtual Ethernet. So as I said, it looks like a normal network node. We do that by sort of working in conjunction with the lower layers, take a TCP stack and virtualize the PCI bus basically as an Ethernet looks like from a software standpoint. And then we have the mic ABI, which James will talk about a little bit. There is a difference between how the ABI works. That's application binary interface, by the way. That's how applications in the OS and the libraries talk to each other. I'm not going to say much about this. This is what James is going to talk about. But again, standard tools are being extended to the Intel mic architecture. You will basically one-stop shop when we launch product. The exact same licensing, purchase options, whatever, will include mic whether you have one or not. So it'll just be there in Parallel Studio and Cluster Studio. They all will be supporting mic. Essentially, as I said, your coding and tuning investments pay ongoing dividends. Again, James will talk about this a little bit. One interesting thing that we found is since both Xeon and mic are parallel devices, and yesterday you were working to vectorize and seeing acceleration, what we found is when you, and then I was talking about dialing up the contrast with highly parallel, right? So one interesting thing is we've seen people who either have, let's call it semi-parallel code or the beginnings of parallel code, and they're really interested in mic and they get started, our customers. And they start making headway. And then they might go and try to compare with the Sandy Bridge or the Xeon. What they find is by just working it on mic, their Xeon code begins to improve and get more vectorized and more capable and more parallel, since that has all the parallel capabilities. So this is really what I meant here by paying dividends is your code that might be targeted Xeon, or you want a portable environment where you go to one platform without Xeon Phis and another one with, you're sort of doubling doubling down and getting better performance even of your code as you really just focus on parallelization. And this is the thing we've been telling people, sort of the opposite. Well, if you can't have access to it because it's a limited program, keep focusing on that parallelization and vectorization and scaling with threading and other models on Xeon. You'll be preparing yourself for Mike. This is kind of a look at the models, that we had in mind, a different view of it. These are the various ways you can work with Mike. You'll see there's kind of a hole here, and that's the hole James just talked about. Normally you would stick the possibility of reverse offload. I just don't have it on here because we don't have a direct environment to do it. But we certainly provided enough stuff for someone to go to town and make their own implementation. If you start on the left here, this is today for anybody in the marketplace. You've got your Xeon general purpose N0 parallel programming. That's what you're working on yesterday. You obviously can just worry about that if that's what's right for your workload or if that's what's available. If you step, your first step, sometimes, and everybody is different how they look at this. One step would be, I've got code, I've got certain kernels. I'm really happy with my code, how it's tuned on Xeon, but I know I'm stuck in Amdahl's law for some of the capability. I want to accelerate a little bit. You can use these offload extensions, which Michael will talk about, but we call it offload. We don't call it accelerate or anything like that. So we have these offload extensions. When you have these parallel phases, then you might want this function to actually go down here and be accelerated. We'll talk about the various ways to use that. And MPI plays a role, if needed, for cluster-wide usage. Or for just MPI parallelization. You certainly can do it alone on the processor. I'm going to jump over here. Many-core hosted, and it's kind of what you were talking about, is we certainly also have the environment where, if you like, other than booting it and getting going, you could create an environment where you just focus. You have highly parallel app. You don't want to spend time on coordinating with Xeon too much. You can create an environment where you can do a cluster-wide Knights only or Xeon Phi only capability that exists and actually is the fundamental. In a way, it's the fundamental baseline. We sometimes call this, you'll hear various terms for it. Here we say many-core hosted or Mike hosted or whatever. We also call that native programming. You're just natively running on the device. And then you have this symmetric one, which also is allowed and interesting. And basically the idea is leverage everything you can on the platform and go for it, right? You can have peer MPI ranks on the Xeon, MPI ranks over here. May or may not be running the same basic code. However, whatever works, might have to do some interesting load balancing there, but leverage the whole platform, get everything out. And in fact, that's what our HPL run did. It leveraged the whole platform. And this is just hammering it home. This is kind of a view, mainly an MPI type cluster view. This is the offload that So I'm not going to hammer this home. Other than do more than we said already, because I know we're running out of time. We call this a homogeneous network of hybrid nodes. This is where you're primarily doing offload, and all your standard MPI messaging that you're used to today occurs over Xeon InfiniBand, and you're using this as an accelerator. As an offload coprocessor, and primarily using that. So that's just sort of works out of the box. This is the other side of the coin I was just talking about. You can have MPI ranks here totally independently with none on here. And talking, one, you can do it between, one thing they don't show here is you could have multiple mics on the platform talking to each other directly as well, sharing data, and then actually going out over the network, InfiniBand or Ethernet, whatever. So that's that mode. I think that's pretty obvious. And then this is the crazy diagram where you can do everything that you want. Every possibility is there. You can have the independent Xeon running stuff, Mike running stuff. Them all talking to each other. So it's crazy slide. But these are all capabilities that are available on the platform. And then this is just kind of bringing it all together, showing you the same slide. And really, I want to point out that we have the breadth of capability and then the depth that you're used to with Intel architecture. All these things are capable across both products and sort of in conjunction with each other. So, you know, on both, you know, so this is a both slide, even though it goes across here. So don't think I'm aligning this or aligning that. This is, you know, you have your ease of use engagement. Again, Neil was talking about, hey, use the math kernel library if you can. We got math kernel library that works in every mode. It works alone on the Xeon, alone on the mic, or leveraging them together. We call that automatic offload. We have an MKL talk, Hans will talk about that tomorrow. You know, Silk plus array notation works right on mic. Don't have to do anything special. The auto vectorization capability, the stuff we were talking about yesterday, the pragmas. We can't show it today. We have OpenCL underway. It'll come later in the project. OpenMP works. P-threads work. You can do a thread pool capability P-threads if that's what your program already does. And you know, continue to drop. You could even drop lower if you want, anything you think of. To the point, I just want to point out, as we said, we open source the Linux environment. You could change that and figure out enough how to bootstrap your own OS. We have at least 2 or 3 customers looking at that. The most prevalent one is University of Tokyo. It's just doing they're basing it on the stuff we give them, and they're just rolling their own highly tuned operating system. So you can rewrite the operating system if you want. So to wrap it up, we view it as an SMP on a chip. The contrast knob, highly parallel applications are going to do well. Heavy serial applications are not. You can leverage it has remarkable raw compute capability. We can do, you know, and the first silicon, again, something that was somewhat unusual for Intel is we brought a lab system that was only about a week old to SC, because that's how long the first part came out, and that part was able to do a teraflop sustained DGEM. And then you know, we've moved forward, and now in the node taking care of that whole environment, we can get a teraflop of HPL. Leverages those existing standards, models, and tools. I probably have belabored that point, but I think that's a huge benefit to the industry. And then again, we preserve and then pay forward. And by pay forward, I mean as time goes on, the more parallel your code is, the more vectorized it is, the more it'll just stay that way and take advantage of the benefits. And you know, I view this as a lot of people talk about disrupting technology. I view this as it's a disruptive in the sense of changing the game, but it's not disrupting. You can, you know, still use what we have. So with that, are there any other questions before we let James jump in? Feel like you have a sense of what this is about? Okay, thank you very much. So what did we do? You know, how did we get where we got? So we, you know, we started with these things we call smaller cores, and you know, smaller in-order capability. Took a lot of the serial performance out so we could leverage that. And obviously, that allowed us to add many processing cores to our silicon. To that, we added very wide vector units. I think we can say it's 512 because it's in the document. So it's double what the maximum AVX size is. And multi-threading. We don't call it hyper-threading in this part. We call it multi-threading. There's some interesting differences between the two. But you know, more threads to take advantage of the memory bandwidth, the latencies that might occur. It's not a panacea. We don't. So let's get started. Okay, so I'm going to give you an overview of the key elements of the architecture. You'll be exploring it today. This is sort of the gratuitous marketing slide. It's maybe it's not too gratuitous, but you know, we just want to confirm that we see an insatiable need for performance. The algorithms up here are from the oil and gas industry, and they already know that they could use an exaflop machine. I'm sure all you guys could figure out that you need an exaflop machine as well, but everyone says, oh, it's going to tail off. You don't need to do all this. Our view is we're probably not doing enough, and that's hence why this growth and the complications of that growth, in particular for power, as David was saying yesterday, the memory speeds, the interconnects are not going at the pace of flops. So I'm not going to say flops are free. I don't think I can say that for Intel. But delivering the whole package is really what we're looking at as well. I'm not going to talk about it much, but Intel, you may have heard that Intel has made significant investments in the last year in interconnect, both essentially acquiring QLogic and then also acquiring the Aries InfiniBand capability from Cray and some of their people. At least I don't know if that's closed yet, but it's been announced. So we're looking at all aspects. But you know, we see no end to the use of, again, both traditional Xeon usages, and then for key power performance improvements, the mic architecture is what we're driving in that area. Pretty much just said it. The Xeon's the foundation. You've all used this architecture. It can handle the full scope of workloads. It has parallel capability. It has serial capability, enhanced, great processor, and new interface or other mechanisms in order to leverage that. It's difficult, but that's one of our goals. And then again, I already repeated, 22 nanometer is the same process that Ivy Bridge is coming out on, and Knights Corner is coming out on that process as well. And the greater than 50 cores, as I said, and again, we haven't said exactly what our product SKUs will have or how many SKUs there will be. So just terminology, Knights Ferry, I already mentioned it. That was an early development platform. I can tell you that we had 2 SKUs of that, both active. See the active fan there. 30 and 32 cores is what we had. That's been well publicized. Knights Corner, again, all these things I showed what the announcement was. They are PCIe cards. They are double wide and GDDR. And then future Knights is how we refer to what might happen next. Most people have great usage of that, including the number 4. The number 4 system is an all Sandy Bridge system, you know, from Europe. The number 1 European system is a full Sandy Bridge Xeon alone system. Just was announced, highly efficient, both power and compute optimized. Xeon Phi, you'll hear this over and over again. Highly parallelized workloads. If you don't have a highly parallelized workload, or it can't be, Phi is not there. Another huge point which we'll continue to hammer home, James will jump on it, is the common programming model. You know, there are nuances about the architecture, and David was showing different architectures yesterday, different levels of cache and all that. But fundamentally, we want the experience to be the same. What you've learned to evolve into the usage, not jumping on another path, a new brand.